Hey, welcome! If you've ever stared at a rotational motion problem, especially one loaded with vectors, and just felt completely lost, well, this explainer is for you. We're going to break down problem 1.56 from the classic Irodov collection. It's a perfect problem for really getting a solid handle on rotational vectors.
Okay, so here's how we're going to tackle this. First, we'll break down the problem statement itself. Then, we'll calculate the angular velocity, and right after that, the angular acceleration. Once we've got those vectors pinned down, we'll find the angle between them. And finally, we'll wrap it all up by talking about the big takeaways. And, super important, the common mistakes that trip people up on problems just like this one.
All right, first things first, we have to deconstruct a problem. And honestly, this is the most important step. Before we even think about touching an equation, we've got to understand what's physically going on and what we're actually being asked to find.
Okay, this is it. This is the heart of the problem. Now, I know it looks kind of intimidating, right? You've got vectors, variables, things changing with time, but don't worry. The trick is to see it as just two separate motions happening at the same time. One rotation around the x-axis and another around the y-axis, that we can look at one piece at a time.
So what does this vector actually mean, physically? Well, the big idea here is that this body isn't just spinning in a nice, simple circle. Nope, its rotation is actually pretty complex. The I component tells us it's speeding up its rotation around the x-axis in a nice, steady, linear way. But at the same time, the J component tells us its rotation around the y-axis is speeding up even faster, with the square of time. This means both the overall speed and the axis of rotation are constantly changing.
All right, let's jump into the first part of the question. We're going to calculate the magnitude of the angular velocity at one specific moment in time. So the problem asks for the modulus, and that's just a fancy word for magnitude. You know, the length of the vector. But here's the thing. To get the magnitude at t equals 10 seconds, we first have to figure out what the vector is at that exact moment. It's like we're freezing time and taking a picture of the rotation.
This is a pretty straightforward three-step deal. First, we're just going to pop t equals 10 into our omega equation. Then, we'll get the actual numbers for the x and y components, and finally, we'll use those numbers and the good old Pythagorean theorem to find the total magnitude, just like finding the hypotenuse of a triangle.
Okay, so let's run the numbers. We've got t equals 10 and a is 0.5, so the x component, at, that's just 5.0. Simple enough. For the y component, bt squared, with b at 0.06, that works out to 6.0. Now for the easy part, Pythagorean theorem, right? The square root of 5 squared plus 6 squared, and bam, we get our answer, 7.8 radians per second.
All right, velocity's done. Now we can move on to the second half of part A, angular acceleration. This is where a little bit of calculus comes in, but don't worry, it's a really simple derivative.
You know, this concept is super fundamental. Think about it. Linear acceleration is just how fast linear velocity is changing, right? Well, it's the exact same idea here. Angular acceleration tells us the rate at which that angular velocity vector is changing. So to get from our velocity vector omega to our acceleration vector beta, all we got to do is take the derivative with respect to time.
Okay, listen up, because this is probably the biggest mistake I see students make on this kind of problem. You absolutely have to differentiate the vector components before you find the magnitude. Seriously, if you find the magnitude of omega first and then try to differentiate it, you're going to get the wrong answer. Why? Because you completely miss how the direction of the rotation is changing, and that's a huge part of the acceleration.
So the process is going to look really familiar, almost exactly like what we did for velocity. Step one is the new part, the calculus. We differentiate the vector omega of t. The derivative of at is just a. Nice and easy. The derivative of bt squared is 2bt. See? Simple. After that, we're back in familiar territory. Plug in t equals 10, and then use Pythagoras to get the magnitude.
So after differentiating, our acceleration vector beta is a in the I direction and 2bt in the j direction. Now we plug in t equals 10. The x component is just a, so that's 0.5. The y component, 2bt, becomes 1.2. Time for the magnitude again, the square root of 0.5 squared plus 1.2 squared. And that gives us 1.3 radians per second squared. And just like that, part A is done.
Okay, we've got our velocity vector and our acceleration vector at that 10-second mark. We know everything about them. So, for the last part of the problem, we need to find the angle between these two vectors.
So, what's this last part really asking? It's all about the geometric relationship between our velocity and acceleration vectors. At this one specific moment, are they pointing in the same direction?
Are they perpendicular, or are they at some other angle? Let's find out.
And the perfect tool for this job is the dot product. You've probably seen this before. It's just a way of multiplying two vectors that kind of tells you how much they're aligned. The formula is what connects the vector components to the cosine of the angle between them. So if we just rearrange that formula, we can solve for the angle. We already have the magnitudes, right? So the only new thing we need to calculate is the dot product itself.
Okay, so here are the vector components we already figured out for t equals 10. Calculating the dot product is super easy. You just multiply the x components together, multiply the y components together, and then add those two numbers up. So it's going to be 5.0 times 0.5 plus 6.0 times 1.2.
Okay, that math gives us a dot product of 9.7. Now, we just divide that by the product of the two magnitudes we found back in part A, which were 7.8 and 1.3. Take the inverse cosine of that number, and we get our final answer. The angle between the velocity and acceleration vectors is 17 degrees. And we're done!
So, we solved the problem. Awesome. But what are the big lessons here? Let's do a quick recap of the process, and maybe more importantly, let's talk about those tricky spots you need to watch out for when you tackle problems like this yourself.
What this problem really shows is that having a system is everything. You always want to start by just understanding what the vectors mean physically. Then follow the steps in order. Get the instantaneous vectors first, either by plugging in time or taking a derivative, and then find the magnitudes. Knowing when to use your tools, like derivatives for acceleration and the dot product for angles, that's what separates getting it right from getting lost.
And here are the traps you got to avoid. I'm going to say it one more time because it's so important. Do not differentiate the magnitude of a vector, ever. Always work with the vector components. Differentiate the components, plug time into the components, and then, only at the very end, calculate the magnitude. If you treat your vectors like vectors, you'll be golden.
And there you have it. That's our full breakdown of Irodov problem 1.56. I really hope walking through it step by step made it all click. Now, to really lock this in, here's a little something to think about. What if we added a z-axis rotation, a k component? How would that change things? Well, the cool thing is, it wouldn't, really. The exact same rules, the same calculus, the same vector math, it all applies. You just have one more dimension to keep track of. Thanks for joining this explainer.